Okay.
I messed up. Even function symmetry across the y-axis, I did the opposite. I did symmetry, symmetry over the origin. So odd is symmetry with like my origin, right? I did
Okay,
the
we
opposite.
begin. Reminder. Test one. That's on March 27th.
Oh, it's Wednesday, like the next Wednesday.
That's next Wednesday.
These
And
weeks are intense.
the date is firm, so the date, that's definitely going to be there. Even if I don't finish all the topics that I said would be on the test, whatever topics we get up to that point, that's going to be on the test. The date is more important than even the topics. So whatever if I didn't get to cover all the topics I said would be on the first test, it doesn't matter. I'm giving you a test on whatever topics we've covered. And so it will cover, let's be a little bit more specific there, cover everything up to Wednesday, as in Wednesday this week, whatever date that is, that's the 23rd, 20th. So that's the first thing. Also, bonus would be on any extra topics that, like, if the syllabus said I would cover it but I didn't cover it, I'll probably just throw it on the bonus. Okay, so the extra topics. Then, no. So, yeah, first test March 27, that is next week Wednesday. It'll cover everything we do up to this Wednesday. Bonus would be on anything we've missed that technically I was supposed to cover or whatever. Then, another thing, review will be a review for the test. Will be posted on Wednesday. Follow the instructions.
Wait, where?
So, I'm not exactly sure what's happening, but whatever is happening in high school these days, it isn't good. I tend to see that students just aren't prepared for a college class as they should be, and so a lot of students won't even know how to study. Like, sometimes I'll talk to students and I'm like, so how did you study for this test? And they tell me what they did, and I'm like, that makes no sense. Why would you do that? So I'm going to tell you how to study for the test. Follow the instructions. But I never used to do it that way. Whatever you were doing was wrong. I'm going to tell you how to study for the test. Follow the instructions. If you are thinking of doing something other than that, you are wrong. Okay, I'll just say that. So I'm going to say, here's the review, here's how you're going to use the review, and if I post any answers, I'll tell you here's how you use the answers to the review, because people don't know how to use these things. Okay, so I'm going to tell you. Okay. I think, other than that, the test would probably be the full period. Like, I didn't write it yet, but just off the top of my head, probably what I would say is it's going to take the full period. Now, the final exam for this class is, it's not like the finals would be for like a calculus class. For the pre-calc classes, the finals, the finals that the department writes, they're usually kind of large in the sense of the number of problems you will be given. So a typical format for the final, I don't know if some of you have taken the class before, you'll realize this, but it'll be something like, it'll have 6 sections with 6 questions each, and you pick 5 out of each section. So you'll end up doing like somewhere between 25 and 30 problems. And so you might have one problem, hey, find the equator line of this, and then another problem, hey, sketch this graph, and then, so each question won't normally have parts to it. It'll just, each question is going to test you on one thing, but the idea is it'll be a lot of questions. That's how the standard is for pre-calc here. And so I'm going to kind of mimic that. So it might not be a full-length final, because for a final you'll have 2 hours and 15 minutes. So I'm pretty much going to give you how many problems can fill an hour and 40 minutes. So you can expect somewhere 15, 20 problems, something like that. Yeah, so roughly 20 problems. Any questions other than that? That's all I can think of. Yeah. Yeah, tests in class, during class. The final I don't know about yet. So the final, they might change the room. The only thing I know about the final is the date, which I did put in the syllabus, but the actual location I'm not sure.
Are the problems going to have
Equal weight?
Yeah,
Yeah.
equal weight.
Yeah. So if I put like 20 problems, it's going to be like 5 points each.
Do you get points for like showing work?
Yes, you will be required to show work. So it won't be like a quiz. It'll be different from a quiz in that sense, which is why you need to follow the instruction. So you haven't been like showing your work so far. So I want to make sure that you're not going to get messed up because you don't know how to show your work. Yeah.
So if we have a certain way to do a problem, when we show our work, you want us to do it the way that you're specifically.
No, I don't care. If it's valid, you can do it. I don't care what it is. So I'll make recommendations from time to time when I'm teaching about, oh, I think it's kind of best that you do it this way, but if you do it another way, it's fine. I'm not a math Nazi. I'm just giving you guys recommendations based on my experience and based on the fact that I've had hundreds of students and I've created a lot of papers and I see the kinds of things that causes students to make mistakes. So I'll make recommendations, but I'm not going to force you to do one way or another. Right? If you want to ignore my recommendations, that's fine. Any other questions? Okay. Let's actually continue. And again, we're still kind of in review mode, so nothing really new going on here. We're going to talk about functions again, and you can see the bonus was on a piecewise function. So we'll also, hopefully by the end of today, we'll get to that, and you'll see how you would do the bonus problem if you weren't sure. So this is now, we're in chapter 2, I believe it's 2.1, so we're going to do functions. Okay. Let's start with the definition. What's a function? What? Yeah?
It's an equation where you can determine one value based on another value. You have to deal with one variable for another.
that's way more specific. You can express a function in terms of an equation, but not always. But yeah, it's a rule that assigns, and this assignment can be made via an equation, but there are other ways it can be made. For us, mostly it's going to be an equation, but I don't want you to think about functions as only equations. Assigns to elements assigns to each element of one set. Right? A set is just a collection of things called the domain of the function. This part is important. It assigns to it exactly one element. In another set. Called the codomain of the function. The elements in the domain are called inputs. The elements to which they are assigned. Are their corresponding outputs. So I've defined the function. It's just a rule that connects things between two sets in a very special way. Every single person in one set is connected to only one person in another set. So as an example, I can diagram a function for you. This is called a mapping diagram. I'll probably talk about it. So we have one set of things here called the domain of the function. And I have another group of things over here called the codomain of the function. And let's say we have three guys living over here. Then there could be some rule that I'm going to say, okay, connect this guy to that guy. Connect this guy to that guy. Connect this guy to the same guy over there. That's an example of a function. Notice everyone over here is connected to someone, and each person over here is connected to exactly one person over there, meaning there's one line going from each part over here to over there. So that's an example of a function. Right? You could have everyone going to a different person. That's also okay. That's an example of a function. How do you know you don't have a function? So something that would look like this. Boom. So that's not a function because this guy's connected to two other guys, right? So you can make connections that are not functions. So function is just a very special kind of relationship. You can also have something like this is not a function. Why is that not a function? Because this guy has no output. A function must connect each person. No one can be missed in the domain. Now, it's worth mentioning that you could miss someone in the codomain. That's actually fine. You could have someone who's not assigned to anyone, but that doesn't break the rules of a function. In fact, sometimes you want to distinguish between the guys that are assigned from the guys that aren't, and this is called the range of a function. Okay, so that's called the range of a function. So for example, I can here have a domain. Over here, I can have the codomain. I can have guys over here, and that's connected to that, that's connected to that, this guy's connected to this guy's connected to that guy, and we have some other guys over here who are not connected to anybody. So the range is this group of people. So if you put all the people that were assigned into a set, that set would be called the range. So that's the range of a function. Now there are many ways to represent a function, so let's talk about that. So as Francisco said, one way is an equation, but it's not the only way. Any kind of relationship you can describe that follows these rules, you can call it a function. So, for example, this is kind of, based on what I've been hearing on the news, this example is going to be out of date pretty soon. But is a biological father of function or not a function? So let's say I take a domain, which is just a group of people in a room, and my rule is connect them to their biological fathers. Is that a function?
Yes.
Right. Every single person is going to have a father. Every single person is going to have only one. Okay, so if I were to say, okay, the relationship is a child of, is that a function?
Yes. No. No.
No.
No, that won't be a function. So going to the parentage way, there's a function, but going the other way is not, because you can have multiple parents, right? So a function doesn't have to be an equation. You can describe any sort of relationship. Once it's described in that way, you're connecting a group of things to a group of other things such that everyone over here is connected to one thing over there. So any such relationship you can describe is a function in the mathematical sense. So oftentimes we'll be working with equations. That's because they're great at abstractions for things, but not all the time. So let's talk about ways to let's talk about some remarks first. Then I'll talk about ways to represent a function. One, we can name functions. Usually, not always, with lowercase letters. So I can talk about f is a function. So I can name a certain function and I can call it the function f. Second, we can represent elements in the domain and range with variables also. So again, usually but not always. Usually we use the variable x to represent a generic input. And we use the variable y to represent a corresponding output. And the notation for saying this is the following. We can say y equals f of x. So me writing down that phrase is the same as me saying there's a function whose name is f. It takes input values x and it outputs values y. Okay? So that just says, in my picture, I can take someone who I can call x to represent anyone over there, and it's going to connect someone to someone called y. Or I can say it connects to someone called f of x if I know the name of the rule is f. Right? So sometimes I don't want to actually write down a function all the time. I just can refer to it by its name. Right? And that's the notation we can use for it here. Okay? So notice this is not a multiplication. This is simply a notation for f of x. You can think of this as plugging the x inside the f. So y equals f of x. This is y equals f of x. I know that's kind of confusing. The word off usually means multiply, but it's not technically a multiplication here. This means the function's name is f. The input is represented by x, and the output is represented by y. By the way, we also give these variables names. The guy that represents the inputs, we call that the independent variable. And the guy that represents the outputs, we call them the dependent variable. That's because technically this tends to come first, and then the answer tends to be what happens afterwards, right? So you think of a function, this is the typical kind of picture. There's a machine that we name f, we plug in things into it named x, and what comes out depends on what we plugged in first. And so that we say that this guy depends on that guy, right? So depending on what I plug in, the function is going to do some rule and spit something else out. So that's kind of the idea. So let's actually start, so those are the general ideas. Let's actually start talking about how you write functions in math. Ways to represent functions. So I'm going to talk about notation, for example. So I can use the notation f colon a to b. This means f is a function with domain a and co-domain b. Right? So if you ever see the language like f goes from R to R, this means I have a function who, when you plug in a real number, the output is going to be a real number. Right? Or f goes from N to R. So this means you plug in a natural number, the output would be a real number. So for example, I can take the square root function would work here. The square root function wouldn't actually work the other way around. Well, we'll talk about that a little bit more. Not terribly important to know that part, but the other things you need to know is that, so this is just a notation thing. Now I'm going to talk about the representations. How you actually write down a function or express that you're looking at a function. One, you can do this via what's called a mapping diagram. Right? So you can literally draw, that's the picture, right? This was called a mapping diagram. So I can say I have a function f let's say this is the domain of f, which is a real number. And over here I have a co-domain of f, which, let's say that's also the set of real numbers. So this guy goes to that, this guy connects to that, this guy connects to that, this guy connects to that. Dot, dot, dot. Right? Remember we write dot, dot, dot when there's a pattern that we can take advantage of. So let's say this guy goes to 2, that guy goes to 2, this guy goes to 5, that guy goes to 10. That's an example of a function. So you can actually just list a bunch of things, and if the pattern is obvious, that's good enough. That's one way to represent a function with a mapping diagram. Two, you can use a verbal description of a function. Right? So describe a function in words. So, example. The above is, how do you describe that function that I just wrote down? Tell me in words what happens to go from one number to the other number. Yeah?
Okay, so the input is inserted.
Yeah?
No.
Just tell me the
It's-
rule. What do
okay,
you do to get
okay,
from this
fine.
to that?
So the input is evaluated by a function to get the codomain.
Yeah? But specifically that one. That one that I wrote down with those specific numbers. Can you describe that in words? A function that will take -1 to 2, it will also take +1 to 2. It will take 2 to 5, it will take 3 to 10. Can you describe what's happening here?
Is it like a piecewise function?
Tell me. What do you mean a parabola? Yeah?
Are you squaring it and adding one?
Squaring and adding 1. That could be how I describe this rule, right? So I could draw a picture. I could also say, this is what it's doing, square it and adding 1, or find the biological father of, or whatever, right? I can say that in words, okay? So square the input, then add 1. That would be in words. And for of course, for the verbal description, word problems show up here. Pretty much a lot of times when you want to solve a word problem using a function, you think of the word problem itself as a description of the function. And so in those cases, vocabulary is important, especially here. Right? So there are a lot of words that translate to math very nicely. So for example, sum means to add, difference means to subtract, product means to multiply, off means to multiply, percent, what does percent mean?
It's a ratio of whatever.
So vocabulary is important, so you should know what the words like sum, difference, product, of, is, percent, right? There are a lot of English words that, etc., that translate directly to some sort of mathematical symbol. So for example, what is percent? Right, so sum can mean to add. It can sometimes mean to subtract. Sum is a general term. When you say difference though, you definitely mean subtract. Product means multiply. Off means multiply. Is means equals. Percent means divide. Just divide. 2% means to divide. That doesn't make any sense. Percent means divide by 100. specifically, right? 50% means 50 divided by 100. 50% is 0.5. Where did that come from? You took the 50, you divided by 100. Okay? So knowing the words are very important because there are a lot of times, funny as it turns out, is that sometimes a problem will actually tell you how to solve it, believe it or not. Right? So, for example, let's see if we can do this now with the words. If I were to ask you, what is 20% of 17? Like I can ask you that question. How would you actually answer that question? Yeah?
You can cross multiply.
Cross multiply what?
As in
These are
20
words.
over 100 equals x over 17.
Sure. Yeah, well that's, you actually took a step here. But you can, like, so someone can ask you, and hidden in the question is the answer itself. So for example, what? I don't know what, I'm looking for it, call it a variable. Is, okay, that means equal. 20, oh, that means 20. Percent, oh, that means divide by 100. Of, oh, that means multiply. 17. So you can literally say x is going to be 20 over 100 times 17, and that's going to be the answer. Yeah.
Or you can also just multiply 17 by 0.8.
Right, well, multiply 17 by 0.2.
No, by 0.8, because you'll get, no, never mind. Yeah.
Yeah, by
I'll
0.2.
think another question.
Yeah, which is what this is. This would be 0.2. So verbal descriptions are important, and when it comes to that and interpreting verbal descriptions, you need to have a list of vocabulary that you would have picked up through algebra and here. So I'm going to assume we're good at these words, but that's just an example of how a verbal description can be helpful. And sometimes a problem is stated as a verbal description because someone doesn't know what to do, and you have to kind of take that verbal description, translate it to an equation, and maybe solve the problem that way. But one way to describe a function is verbally. And sometimes this is so helpful that the answer is hidden in the question itself. Other times you kind of have to work for it a little bit. So that's a verbal description. But here the language that we use really kind of lends itself to mathematical operations, right? We're talking about squaring and adding something. So that kind of reminds us of another way that we can describe a function. And this was the first way that was mentioned by Francisco, via a formula or an equation. And so this is sometimes called algebraically. This means via a formula.
Actually, that would be number 3, because we already said
3. Yeah. I erased the equation. Okay. So example. Let's talk about the same one above. Right, the original one that I had here. We said we squared it and add 1. So how could you actually describe that?
f(x) equals x squared plus 1.
Right. So that same idea, the one that I sketched with a diagram, the one that I described in words, in this case can somehow be described by a formula. Right? Now, not everything can be described by a formula, but a lot of times it can be. Right? And math is especially useful in the case that you can describe what you're talking about with a formula like this. So that's another way. Right? Or you can say y equals x squared plus 1 if y is the dependent variable. So you can write it down as a picture, you can draw a diagram of things connecting, you can say it in words, you can actually use a formula a lot of times. Another way is via graphing, which we spoke about what a graph is. It's just a pictorial representation of a function. Basically, if you plot all the possible points that fit this equation, that make that equation true, you get what's called a graph. And that picture is very helpful in answering a lot of problems very quickly. And you can talk about, after that, the behaviors of functions and what a graph can tell you about a function. And that can help you solve problems as well. So in this case, so this is a picture of the function. Equation on the Cartesian axis. Now I described in general what that is, and I told you how to graph a straight line. We should kind of already know how to graph a function, so a quadratic. So let's actually look at this one. What would that look like?
Parabola going infinity up.
Okay.
Up,
Tell me a point that it goes to.
0, 0, 1.
Right. So like that. We'll talk about how to get graphs like this soon, but it looks like one. So that would be the picture. And so, for example, someone can describe this function to me. They might first tell me a picture or tell me in words, and what I can do is I can come up with an equation, then I can draw a picture. And now when I have the picture, there are a lot of things I can talk about this rule right away. For example, I can say, oh, the minimum value is going to be 1. It will never give me a value less than 1. Right? And I can just look at that from the picture. And then I can also say, oh, there's going to be no largest value. It'll keep just getting bigger and bigger and bigger. Right? I can talk about what the rule means in the real world, what does it imply, what the consequences are of such a function. And so here we can talk about a lot of stuff. Right, so that's one reason why graphs are important. So for example, I can say the minimum is y equals 1. I can say there is no maximum. I can say something like, oh, -1 is not in the range, right? In fact, I can say any number smaller than 1 is not in the range, right? I can talk about this function, right? Now, the function itself is typically not what you would care about. I know none of you actually care about x squared plus 1. What's important is what the function represents to you, right? So these are questions that a picture can really help us answer when the function is really measuring something we care about, okay? So you have a function measuring the amount of money in your bank account. You want to know when it hits a bottom versus a high. Or measuring the profits that you get per week in your business. I want to know, when was I making the most profit? When was I making the less profit? What was going on around this time, right? So you can track certain things by functions, and a lot of times then drawing a picture of the function can get you to talk about the situation that you first described with the function. And then you can kind of figure things out, how you'd want to attack things in the real world by looking at the picture. Right? So pictures are very helpful. It's a very useful way to graph a function, to represent a function. And in fact, in a math class, these two are really kind of the important ones. So you would tend, if you're given a function in another form, you tend to want to be able to express it in one of these two forms in order to answer some question about the function. So these are the really important ones, right? If you can describe something by an equation or a graph, that's good. You will tend to be able to answer the questions in this class. There's another way via coordinates, or it's sometimes called ordered pairs. So for example, in the above, I can say f is the set of these coordinates, right? So I can say 1 minus 1 goes to 2, 1 goes to 2, 2 would go to 5, and I would say something like 6 would go to 37, dot, 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 right? And I can describe that as a set of things. And each of these guys is called a coordinate, or an ordered pair. So this entire object here is a coordinate, or ordered pair, because there's a pair of things in a certain order, where the input values in the first one and the corresponding output values in the second one, in the second position. Okay? So you know when you're looking at a function, it would mean that once the first value appears here, it can never appear as the first value anywhere else, because that means -1 is connected to two different people. So every person in your domain needs to show up in the first position one time, and only one time. So if you have one number showing up several times in the first position, what you're looking at is not a function, as well as if you know there's a domain and there's someone in your domain that doesn't show up in the first position, it's also not a function. But ordered pairs is another way you can express a function. Those are some common ways. 3 and 4 tend to be the ones we want to use the most. Another way that's useful sometimes. This is probably the last one that I'll talk about. And this can be useful sometimes. Especially, even in calculus, I kind of use this way recently with my class to figure out certain problems. And it's just by a table of values. So, for example, again, I'm using the same function as an example so you can see how I can express the same function in various ways. I can create a table of values with 2 columns where I put the x value and the y value, and I can just list off a bunch of guys. And sometimes examining that table can help me solve a lot of problems. So I'll know, okay, -1 will go to 2, 1 will go to 2, 3 will go to 10, 6 will go to 37, dot, dot, dot. So I can talk about a table of values. And sometimes even that table could tell you a lot, because you'll notice no matter how you fill out the table, you'll never get a negative number over here, for example. And you can notice that from a table. There's no negative sign over here. Okay, so that's ways we can represent functions. 3 and 4 tend to be the most useful representations. At least in an algebra class. I mean, if you're in a statistics class, probably the table and the picture would be the most useful, like 4 and 6. But for us, and in all your calculus classes, you kind of want to go to a situation where you can express it as an equation or express it as a picture. Okay, let's talk about evaluating functions. And maybe I'll also talk about piecewise functions at this point, so you can see what the bonus would have looked like. Now, this is an idea that is deceptively simple. A lot of students think they know how to evaluate functions, most don't. And I'm going to... Will I have time to show you that? I'm eventually going to show you a situation in which students tend to mess up a lot. That is with computing a difference quotient, for example. Students miscalculate that a lot, and it's because they don't understand what it means to evaluate a function. So pay attention. The idea is going to be simple, but it's deceptively simple, so pay attention. To evaluate a function, at some input means to find / compute the corresponding output. Or that input. Algebraically, remember, algebraically just means the situation where you're looking at an equation. Algebraically, this is done by replacing the independent variable with the particular input. And that's always how you want to think about it. I'll probably mention in words another way you want to think about it, right? But you want to think about it as a replacement. You're literally swapping someone out for someone else. So, let's look, for example, again, using the above function. We had f of x equals x squared plus 1. So I can say evaluate f at x equals 2. This means find f of 2, right? And what that means is you are going to replace the x in f of x with 2. That's it. That's the idea. Students mess this up all the time. I'm not sure why, but they mess that up all the time. You literally look at the equation. Everywhere you see an x, you are now going to write 2 instead of that x. Okay, so here's a way to think about it. You want to think, it's better to think of your functions as templates where the independent variable is simply a placeholder for something that's going to replace it eventually. I want to spend some time on this because I know people are going to mess it up. Even when I warn people about it, they still mess it up. But I got to do what I can do anyway. Another way to think of it. The formula is a template the appearance of the independent variable is a placeholder It's a very important idea. Expressing it another way. If you see this, think this. Imagine that the x is not even there. There's a void there that you can drop something into. The x is a placeholder, that's all it is. Right? Whatever you drop here gets dropped in there. Right? So you want to think of it as the x is just telling you about a place that you can evaluate something. right? So this is just a placeholder for the point where you want to evaluate. So, to go back to this example. If I say f of x is x squared plus 1, and I ask you to find f of 2, the first thing you're going to do, you're not going to write this down, well, at least not completely. You might think of the first step. The first thing you want to do is you think of this. 2, put 2 in the space. Okay? So you look at that in your mind, you should see this. And then the 2, everywhere I see an x, I now put a 2. Do we understand? Am I losing it? Okay. You'd be surprised that people mess up all the time. I'm not sure why. If I was like into math education, this would be a topic that I would research. Why does the brain mix up this simple idea? Like because it's a very common thing to mess up. And I don't know why, but it is for whatever reason. So, do I have any other examples here? I don't, but I feel like it's worth doing some more examples. Okay, example. What would f of 3 be? So I tell you, that's the rule. So just stay at 7. Why? There was no x to replace, so I literally just copy it back. Okay, let's say I have f of x equals 3x squared minus x plus 1. And I say evaluate. Of minus 1. How would you do that? So you get that. And then you compute that as, well, -1 squared, follow PEMDAS, that's still a thing. Anything I tell you at any point will always be true. Okay. Sometimes you get to something more complicated and students forget all the symbols. Okay, so -1 squared, you get +1 times 3, that's 3. Minus the negative, that's +1. So it's 3 plus 1 plus 1, and that will be fine. Okay. What if I asked you about f of a? What is f of a?
You just plug in 3a squared.
What if I asked you f of a squared?
3 parentheses, a squared, close parentheses squared, minus parentheses, a squared, close parentheses plus 1.
What if I asked you f of x plus h? Huh?
Plus minus. Parentheses, f of h.
next to f of smiley face.
Smiley face.
It's a scale.
Square. Minus, open parentheses, smiley face. Plus 1.
Whatever shows up here replaces x in every position that it occurs. Okay? So I'm announcing what I'm about to show you, you should never do. Okay? It is not something to do. Okay, this is an example of what not to do. Okay. So let's say you had f of x equals 3x squared minus x plus 1. And I asked you to talk about f of x plus h. Okay? It is very common for a student to write that expression. Okay, do we see the problem? Okay, so this left side here, what you have done is you just copied f of x and then you added an h separately. It is not the same as f of x plus h. Okay. So something like that, do not do. So when we see something, I'm going to talk about this one specifically because it shows up all the time. So I'll probably memorize this. Like I keep trying to come up with ways. So that ends the common mistake. I keep trying to come up with ways to actually bring this across because somehow it doesn't get across. I'm not sure. Okay. Memorize this phrase. F of x plus h means everywhere I see x, replace with parentheses x plus h. Okay? That's the phrase. I just read that sentence, read it over and over and over and over. Even if you don't think you need to, even if you think you got it, make sure you memorize that sentence. We'll stop there, we'll pick up you more information, talk about some graphs, maybe quadratics as well. Maybe back here in quizzes on Wednesday. Great.